All right. Yeah. Our color is orange. Usually we wear orange, but the special occasion is somewhat different for us. So, yeah, you know. Anyhow, we were wondering ourselves, how can we improve the network reliability? And it turns out that we have a device where we can directly read out of the memory of the transceivers, and it is interesting what they tell us. So this presentation was created by Thomas, the CTO, and myself, and let's talk about network reliability. So bit error rate dependency. So bit error rate dependency, to make all this a little bit more interesting, we have a couple of parameters. We have distance, we have temperature. We don't like high temperature, as you know, a lot of energy, and you have to take out all this energy. And now you see here black squares. Because this presentation is quite long, we decided to split it up, and the second part will be in 2 months. So we are going to travel, and there will be more exciting topics related to this, but also with other observations regarding energy consumption. So yeah, transceivers, especially coherent one. We heard a little bit about coherent one, but we also have still a lot of these classical, we call them direct detection transceivers. And what is interesting of transceivers nowadays, that just one of these small plugs has a chip on it where you can, it generates the signal. Obviously, it has to modulate, it has to turn on the laser, but there's even more what you can do. Forward error correction, we know what it does, but also bit error rate. So you have an integrated bit error rate tester, and you can measure bit error rate. You can measure OSNR, the optical signal to noise ratio, and that is quite interesting because here we see 2 point of views. We have the point of view of a network operator, a person that is interested in data. We want to have the highest bandwidth. If I have a 400G transceiver, I want to be sure I get 400G, or at least as much as possible. It depends also a little bit on the attenuation in the line, and that's one point of view. But the other point of view is also signal quality. So we have here like these 2 point of views. You have a certain requirement for signal to noise ratio. What is this exactly? It's a relation between noise and signal, useful signal, which means if the noise goes up, it is the effect when the audience, you're a good audience, you're very silent and listening to me, but if you would have been shouting or talking, you cannot listen to me anymore because it's too loud, so the noise goes up. And a very good value here is the signal to noise ratio. If you have too much noise in your line, this relation goes down. So you want to get the useful signal, and with that you can get your data rate you require. So this is our FLEXBox. This is my setup. I had to cut off the head and put a heatsink on it. Here you see an 800G transceiver. I cannot show all the results, but I want to show you the most interesting curves and a little bit of discussion. So yeah. These are the transceivers I tested. So 100G, 400G, 800G, 1.6, we are about to get it. I will test this as well, but it didn't make it into the presentation. But these transceivers are capable to read out a lot of data from the EEPROM, from the memory. And in order to measure bit error rate over longer cables with different distances and also different temperatures, what you have to consider is your setup. Because there's one thing. If you have a transceiver and you want to measure it on long distances, we usually have these cable trumps. You can tie them together with some couple element, but you have to watch for your attenuation, because if you buy a transceiver like this one, the 100G QSFP ER28ER, and if you connect a 2-meter fiber cable, you have to connect an attenuator. Why am I mentioning this? Well, the reason is, if I want to measure 2 meters, then 10 kilometers, and 60 kilometers, I have to put attenuators. So like I'm adding another parameter, and that makes it a little bit more confusing. Because normally when you want to measure correlation, you want to keep your number of parameters as low as possible, but here it is not possible, because if I don't use any attenuation, I might destroy the receptor, the photodiode. So you can look this up, you can check the total attenuation you have to consider for your transceiver. In this case, if you check the maximum and minimum value, we have about 11 dB. So I started with 11 dB. In order to keep it comparable, I have 3 cases with 11 dB, the 2 meter, the 10 kilometer, and the 20 kilometer one. But after that, I didn't get any signal, so I started to reduce attenuation by removing basically attenuators. You can combine those pretty well. So, and this is the diagram we have, and yeah, a little bit complex, but what is the most interesting aspect here? The red section you see, the 2.4 times 10 to minus 4, is the region where it is considered by IEEE standard. It is a limit you have for Ethernet connectivity. Now, if you check bit error rates, usually they are way lower. This is the limit. It does not mean that you have a good bit error. You have a high bit error rate, but you don't have a good bandwidth. So that's the thing. So with this transceiver, you can use 50 kilometers with high attenuation, but as you can see, it's already in the red section. But what is more interesting about this diagram, there isn't so much correlation to the temperature. With some exceptions, like you have some jumps. If the temperature goes up, all of a sudden it jumps down, and the bit error rate is better, which could be the conclusion that, well, if you heat up your transceiver, the bit error rate is better. Nah, it doesn't make sense, right? Well, it turns out that what we do in the manufacturing is checking the eye diagram. To explain it briefly, usually you have, in the ideal world, your rectangle signal. So if you have a high signal and a low signal, you can assign ones and zeros, and that is how it works with direct detection transceivers. And if you have an oscilloscope and you go as fast as the oscilloscope in your relative velocity as your bandwidth, you end up seeing like also rectangle, because everything is drawn on this display. This is the ideal world. Realistically, you have curves, obviously, and if you join all these curves together, you get to see an eye. That is why it is called eye diagram. And what the manufacturers do is checking this eye diagram everywhere, every time the temperature goes up. And if they are not satisfied with this eye diagram, you know, for a good eye diagram, it has to be symmetrical, and it must not have too much noise, and the curves must be how it is expected. If this is not happening, they start to correct parameters, especially bias current. It's the current that flows into the laser. So if they do that, it all of a sudden also changes the bit error rate. So please keep this in mind if you start measuring the bit error rate. Now, I already showed you this formula. Unfortunately, we have to talk a little bit more about mathematics. There's no other way around. This is applied to our bandwidth, and it is a term that is used pretty often. It's called the gating time. Now you could say, well, delta t is my gating time, and I just put it on the left side, and with the bandwidth I know what the gating time is, but what does it really mean? The problem with the gating time is when you start measuring bit error rate, also your measurement apparatus might give you mistakes. So if you measure an error, you think it's an error, but in the end it's not an error. So you have some Gaussian noise, it is called this effect. And in order to avoid this Gaussian noise, you make an assumption. You better send, instead of waiting for one sample that has an error that could be erroneous, could be wrong, you send 100. And the probability is higher that of these 100 errors, some of them are really errors. So that is what they call gating time, and sample of 100 is what you usually do. And if you assume 100 gigabits per second, your bit error rate is with 2-meter fiber, typical transceiver, you have 10 to minus 12. Your gating time is about 16 minutes. So you should wait 16 minutes and just observe. That is the point where you can assume, well, this is my bit error rate. Can I live with it or not? Up to you to judge, right? And if I put the value from the EEE, with the red area you saw, you get a time of 4 microseconds. Quite interesting how different it is. 4 microseconds compared to 16 minutes. So there's a lot you can do with a bit error rate, what can happen and how fast you can have a good quality or not in your fiber. So here we have a coherent transceiver, another setup I tried. This presentation is about comparing coherent. We heard about coherent transceivers in the morning and direct detection. To recapitulate this a little bit, direct detection with eye diagram, I explained a little bit. The coherent uses polarization effects and phase shifting. You don't look at an eye diagram. You could do it, but you would have to split it up. It's a little bit more complex, so that is what is the difference of these technologies. But the advantage of having more complexity also means you can transfer more data in the same plane at the same baud rate. So that's a little bit of the idea, but it also means that these get way hotter than the direct detection transceivers. And yeah, just as a small, like in Bavaria, Germany, we say Schmankerl, our CTO has a good relationship, a friendship to a person in Frankfurt that collects old switches, old routers. If you have something you want to throw away, please don't throw it away. We like to recycle it, and if you're interested in such project, he recovers copper usually, but also gives us something, or can also give you some disassembled components. For example, in my case, I got this heatsink, which comes from an old Cisco router. If someone from Cisco is here around, thank you very much. These are quite good. I like them a lot. They pull out a lot of heat. And yeah, now we have a difference compared to the 40 kilometer direct detection one. As you can see, the temperature does not affect those. Why is that? Well, I was able to remove one parameter because the coherent has another advantage. Here I don't need attenuators. I did not attenuate that one, and here you can see if you can reduce the number of parameters, it's better. So more complex transceiver, but easier to record and to compare, better to compare, more comparable. And as you can see, the temperature is not really our enemy here, or our problem. Problematic is really the cable, the length of the fiber cable. Now you see different values with bit error rate, and it's a different kind of transceiver. The coherent can live with higher bit error rate. It's a different specification, and due to their local oscillator and kind of fact that is being used, the forward error correction, it can deal with higher bit error rate. So that is fine if you are in the range between 1.5, 10 to minus 4, and 10 to minus 2, which I consider high. I'm impressed, but it still can correct, and it works up to 60 kilometers. So this one was specified, if I remember, for 48, and it can still do 60. But yeah. Another experiment we want to try out, because temperature is our problem, as I mentioned. We wanted to see limits of the transceiver, because usually if you look at your switch, you can see high warning and high alarm temperature. But what does it mean? What does it mean if you go beyond high alarm? So we wanted to test this out and heat our transceiver. And by the way, I brought this transceiver. It's the same transceiver I have here. So what you see here in my experiment is a small barbecue party. We wrapped some aluminum around our flex box, so 120 degrees. Yeah, it's a little bit problematic. We just exposed the transceiver, and I used the heat gun with that. That can go up to 600 degrees. So it's dangerous. You have to be careful with that. And we started to observe how this transceiver behaves. And here you can see in these lines, high warning, high alarm, that is what you, these are the values, the thresholds you can read from your network gear. And I wanted to just press these values and see when the link gets lost, because that is quite interesting what margin we still have. Do we have to remove the transceiver? Do we have to trash it? Does it still work? And I tried this in different phases, since we also have some secures here. And with the warm-up, I just left it running for quite a while, then it canceled after 65 degrees. That is the temperature we usually take. We try to be very secure in this aspect. Then I removed the secure and rebooted it, and then it passed. And as you can see, up to 100 degrees at 80, it loses the signal. So it is lost. I turned everything off. I tried it again with 120 degrees after briefly cooling down. It worked, but around 80 degrees it gave up, loss of signal. And yeah, so I know this transceiver still recovers, but I wanted to see if it can go back to the bit error rate I had before, if I damaged anything with the 120 degrees. And it turned out after my cool down exercise, I still am hitting the curves of the previous one with 100 degrees. So this transceiver is still operational, works. And I think this is, these are good news. But yeah, you shouldn't do this too often. Anyways, bit error rate, is it recoverable? Well, the thing is, the bit error rate is also a rolling average, which means when you read it and you change something in your environment, like heating up your transceiver because you removed the fan or the cooling, it does not go down to the original value because you are tracking history. In order to prevent this, you might have to reset your transceiver, and that is what I'm showing here. So I removed the cooler, waited a little bit, put it back. As you can see, the temperature goes down again. It stabilizes, but bit error rate never stabilizes. But this is not a bad sign. As soon as you reset the transceiver, you're all good. Just to keep in mind. And with that, we're ready for the small experiment. Let's go. Do we have time? Hope I wasn't too fast. By the way, if I'm too fast, please shout slower. It's all right. I have this tendency to talking too fast. All right. More than enough. Awesome. And let's do a little bit of Python goodie. And here we go. So live demo of bit error rate. So our FLEXOPTIX can read it. It takes a little bit because the transceiver is booting up. You can compare it a little bit with the computer. There's almost a computer inside. It's an MCU with a DSP. So you could say it's booting up. Of course, it's not Windows. It's a different kind of operating system there. Yeah, but it takes time to come up. It has a bootloader, and not just that, it is also writing the proper diagnostics. And yeah, it's still a little bit busy, but give it a little bit of time, the curves then will appear. So what are we looking here? The bit error rate I have been talking about. There's host and media. If you have a switch, the host bit error rate is triggered by the switch itself because it generates the signal there. Media is when the transceiver triggers the signal, so we are really using the DSP on it. Temperature is being measured, X power, so you can see how my fiber reacts. And of course, OSNR, I haven't talked so much about it, but it's also interesting to observe, you know, the relation between signal and noise, optical signal to noise ratio. And as you can see, it stabilizes a little bit. The temperature obviously goes up. It gets warmer. With this is a 100G transceiver. With a coherent transceiver, it heats up way faster because of the already mentioned reason with the complexity. Now, to see what happens if the signal gets lost, maybe a question to the audience. What is the lowest dB signal you can expect at X power? Has anybody an idea? If I bend this cable, what value would you get? What would be the theoretical minimum if there's no signal in dB? Minus 40, yeah? It's not the theoretical minimum. theoretical is infinity, of course, but 40 is the conventional value to consider, because after that, I mean, you only have noise and you don't need to consider anything. And let me see if I get the 40. I'm close. Just to see how it relates to the rest. So you get already 1, the bit array, you have only errors through this line. Ah, here we go, 40. It doesn't go lower than that. But what is interesting is the optical signal-to-noise ratio. It improves if I do that. That's quite interesting. This is a default value the manufacturer likes to transfer, like the highest value possible, because the optical signal-to-noise ratio, if you observe it, has to be between 20 and 30. If it goes beyond 30, it is bad. Why? Because you have another effect. What you are expanding with more light intensity is a quantum effect. It is called quantum noise, and that is the reason why you have to keep a certain level. It's not good to have too much signal-to-noise ratio, hard to believe, but being too low because it gets worse. That's the reason why you get this diagram. So this is like a minus infinity or value like that. Yeah. Anyway, let's go back to the slides. So we were not satisfied. We tried another transceiver. Since 120 it survived. We really wanted to see the extreme. So how far can we get? And we tried another experiment with 250, was a smaller transceiver, but you can also read out some values just out of curiosity. And it's interesting to observe, if you read out the memory, there's this 128. I just called it weird because, yeah, what does it mean? I got negative temperatures. Now in this curve it is correct already because I flipped the sign, because your first bit is, you have a 8-bit value you are reading, but usually it is a signed char in C, like sign char it is called, and the first bit indicates the sign. So it is considered in the standards of the transceiver that you never trespass the 120 degrees. We did that, so we got negative temperatures, which doesn't make sense. But anyhow, we lost the signal, we went beyond, and what happened here was we really destroyed this transceiver. As you can see, the label, not even the label is readable anymore. The FLEXOPTIX survived it. It's still doing more or less well. The port behaves a little bit weirdly, but there's still contact. But this transceiver, forget it. What happens? The IX signal goes way down. It's still a way you can read. You could assume it works somewhat, but don't use this transceiver anymore. Yep. And yes, that's it from our side. So we have bit error rate on direct detection transceivers, eye diagram, and they depend both on temperature and fiber length. Bit error rate is always a rolling average. Keep this in mind if you are seeing it on your network gear and you try to influence this through different methods. The margin is not, after the high alarm and the loss of signal, there's not so much margin, so respect the high alarm that is being indicated. Coherent transceivers benefit of more properties of the light, like polarization and phase shifting. So it has a good signal recovery, so you don't have to worry so much about temperature, but fiber length is where you have to look for how, what bit error rate you get in the end. And yes, that's basically it. No presentation is complete without AI, so we try to generate some AI pictures. Now they are already 1 year old, but I thought, yeah, Chinese takeaway restaurant filled with transceivers. They look a little bit strange, I'd say, and not sure if it is electrical or optical cable. But anyways, that's also part of, would you call it creativity? No, inference is better, I'd say. Thank you very much.
Thank you, Gerhard. We have some time left. Are there any questions for Gerhard? Anything from Menti? We have something from Menti. Yes.
Yes, so we have someone asking if they can play with this on any older Flexbox.
I cannot.
Can you ask the question one more time, please, Tor?
Yes.
Can you repeat?
There was someone wondering if they can play with this on any older Flexbox.
Older Flexbox. No, this is the latest FLEXOPTIX. There's no support for the older one. Theoretically, there would be support, but I mean, you need to access the codes, and the limitation with the previous FLEXOPTIX generation. The thing is, we don't have DD on the older FLEXOPTIX. There's a socket, yes, you can extend it. So it would be possible, yes, but we never looked into this because our focus is on the newest product. But to answer your question, theoretically, yes, it is possible since you can read out the EEPROM, and yeah, it would be a feasible. Interesting question, by the way.
Any more questions for Gerhard?
Yes.
Oh, okay, yep.
So we have another question, actually. So you need to update your Mac. Thanks for an interesting talk.
You're welcome.
Okay. Okay, I think on that note, we should say thank you for an amazing presentation and a brave live demo.
Thank you. Thank you. It was a pleasure.